In this video, we'll continue our look at energy. We'll be looking at conservation of energy. We'll state the principle of conservation of energy. We'll state exactly what it means when we say that energy is conserved. And we will look at situations in which the energy is conserved, and we'll apply the principle of conservation of energy to certain situations. So let's talk about energy conservation. Now, usually, when you hear the term to conserve energy, it generally means not to waste it. So for instance, if you're at home and you have all the lights on at the same time, you have the TV playing, the radio playing, the computer on, your parents normally tell you to turn off the lights, turn off the TV, and that you should conserve energy, right? So in that context, the word conserve basically means not to waste. However, what we will show later is that in physics and in science, energy could still be conserved while being wasted, right? Another situation, if you're running a race, let's say you're running a long race, a marathon. You don't want to sprint for the first 100 meters because, of course, you'll be using up a lot of energy quite rapidly, and chances are you won't be able to finish the race if you do that, right? So in those situations, when we speak about conserving energy, we basically mean not to waste it. But in physics, when we speak about energy conservation, it generally means something different. So we will look at the principle of conservation of energy. So, principle of conservation of energy. Right? Now, according to the principle of conservation of energy, it basically states that energy can neither be created nor destroyed, but can only be converted from one form into another, right? So that is what the principle of conservation of energy states. So I'll repeat. According to the principle of conservation of energy, energy can neither be created nor destroyed, but can only be converted from one form to another. Now, what exactly does this mean? Now, this is basically saying that the total amount of energy in the universe is fixed. It is constant. We can't add any to it, so we can't increase it, and neither can we take any away from it. We can't decrease it, right? The only thing we can do is to actually convert some of that energy from one form into another. But at the end of all of those conversions, the total amount of energy basically remains the same, right? So in previous videos, we have mentioned that the sun is the ultimate source of our energy, and of course energy from the sunlight is absorbed by plants and used to make food by the process called photosynthesis and so on. So whatever amount of energy is being supplied by the sun, then we can't increase it, we can't decrease it. All we can do is basically convert that energy from one form into another, right? So this is the principle of conservation of energy. Now, when it comes to questions, the principle of conservation of mechanical energy is basically what is more applicable. Now, when we speak about mechanical energy, what do we mean? Now, collectively, when we speak about mechanical energy, when we use the expression mechanical energy, we're talking about kinetic energy and gravitational potential energy. So kinetic energy and gravitational potential energy are collectively referred to as mechanical energy. And in questions, the principle of conservation of mechanical energy is basically more applicable. So we'll go ahead and we'll state the principle of conservation of mechanical energy. Now, according to the principle of conservation of mechanical energy, the total mechanical energy in an isolated system. Total mechanical energy, let me just insert that. Of course, by that we mean kinetic, some of the kinetic energy and potential energy in an isolated system is constant. Right? Again, this means that the total amount of mechanical energy will not decrease. It remains constant. Right? In simpler words, or in other words, the loss of potential energy is equal to the gain in kinetic energy, and of course vice versa. Right? So this is basically what the principle of conservation of mechanical energy states. So we already looked at the principle of conservation of energy, and it says that energy can neither be created nor destroyed, but can only be converted from one form to another. Right? Now, as I mentioned before, in our mechanics problems, generally it is the principle of conservation of mechanical energy which is more applicable. And when we speak about mechanical energy, we're speaking about kinetic energy and potential energy collectively, right? So kinetic energy and potential energy are collectively referred to as mechanical energy, right? And of course, when you say potential energy, we're talking about gravitational potential energy, right? So the total mechanical energy, so EK plus EP in an isolated system is constant, right? For now, we're not going to pay too much attention to isolated system. That's just right. So what we need to be able to do is to just apply this principle to questions. So in other words, then this basically means that the loss of potential energy is equal to the gain in kinetic energy and vice versa, right? So we will now look at a few situations in which this form of the principle of conservation of energy applies. Now let's try to think of a situation in which a body is losing potential energy and gaining kinetic energy. The simplest situation basically is, for instance, an object which is going to be released from a certain height. So for instance, let's talk about a ball which is released from some height above the ground. So we say consider a ball, let's say of mass m, which is released from a height h above the ground. Right? So let this be our ball. Right? That's our ball. And let this be the ground. Right? So the ball is at a height h above the ground. Right? Now let's think about the energy possessed by the ball and so on. Now the ball is initially stationary, so it is held. So similar to how I'm holding this eraser, the ball is initially held at some height h above the ground. Now in that situation, or in that position, it possesses gravitational potential energy EP given by mgh, right? Now let's think about what happens as the ball is released and it falls. Now, since it is stationary, of course, the initial velocity, of course, the velocity, of course, is 0. So now the velocity is equal to 0. And if the velocity is equal to 0, then this further implies that the kinetic energy is equal to 0. So remember that kinetic energy is the energy a body possesses due to its motion. And so if a body is stationary, the velocity is 0, and therefore its kinetic energy is 0. So at the top, the ball has potential energy, and the kinetic energy is 0, right? Now, when the ball is released, as it falls, naturally, it loses height. So it gets closer to the ground as it falls. Now, as it falls, it loses height, and therefore its potential energy decreases. Now, if we ignore the effects of wind resistance, then any decrease in potential energy will result in an equal gain in kinetic energy, right? And this is basically what we mean by the conservation of mechanical energy. So if the potential energy decreases by a certain amount, then the kinetic energy will increase by that equivalent amount, right? So again, as the ball falls, its height decreases, and so does its potential energy. The speed increases, and so does its kinetic energy. And if we ignore the effects of wind resistance, we say that the loss of potential energy is equal to the gain in kinetic energy, right? So again, as the ball falls, its height decreases, it loses potential energy, and it gains an equal amount of kinetic energy. Now, eventually, when the ball reaches the ground, then the potential energy at ground level, EP, would be equal to 0, right? And of course, it acquires a velocity v, and the kinetic energy, EK, of course, is equal to a half mv squared. Now, we say that the mechanical energy is conserved, and therefore the total amount of mechanical energy possessed by the ball will be constant. Now, what exactly does this mean? Let's put some numbers to it. Now, let's say, for instance, at the top, at the height h, the ball had, say, 500 joules of potential energy, right? As it falls, it will lose kinetic energy, and eventually when it strikes the ground level and the potential energy is equal to 0, then the kinetic energy it now possesses will be equal to the initial amount of potential energy. So at the ground level, it now possesses 500 joules of kinetic energy, and the potential energy is 0, right? At any point between the maximum height and the ground level, the potential energy and the kinetic energy is still equal to 500 joules. So for instance, if at some point the potential energy is, say, 200 joules, then the kinetic energy will be 300. If the potential energy is 100, then the kinetic energy is equal to 400, right? So because initial potential energy possessed by the ball is 500 joules, if we ignore the effects of wind resistance, at any stage during its motion, the total amount of energy possessed is 500 joules. Now, having looked at that situation involving the ball, we will now look at another situation, and this time we'll look at that of a situation involving a simple pendulum, right? Now, however, before we actually go on to that, if we were to reverse the direction of motion, so let's say, for instance, the ball was actually thrown upwards initially, then that would mean it would have a large amount of kinetic energy, and as it rises, it loses kinetic energy at the expense of its potential energy. So it loses kinetic energy and gains an equivalent amount of potential energy. And once again, if you ignore the effects of wind resistance, then it means at the maximum height, it will now possess the same amount of potential energy as kinetic energy it initially possessed. So in any direction, the principle of conservation of mechanical energy would still apply. Now, let's look at the case of the simple pendulum. Right, so let's say we have simple pendulum, which of course is just a metal bob attached to a piece of string, right? So this is simple pendulum. So the pendulum is released. My diagram is not, my arc is not perfect, but I mean, you're supposed to get the idea. Let me try to make it a little bit better. Try to make it symmetric. About a half there and a half there. About there. All right, that looks a little bit better, does it? Symmetric. Could be a little bit further, but anyways, you get the idea. Right, so let's look at the pendulum. Now at this level, we call it, this is basically the equilibrium position. So this is the equilibrium position, right? Now the pendulum is basically released from a height h above its equilibrium position. Eventually it falls to its lowest point and it returns to the initial height from which it was released, right? Good. So this is a case of our pendulum. Now let's say, well, this is the point of connection, right? So this is a pendulum, right? So at this position, so the pendulum is released. Let's call this point A. So this is point A. This is point B. And this is C. Good. So the pendulum is released from point A and it's at a height h above what we call the equilibrium position. The equilibrium position, of course, is the lowest position or the lowest point through which a pendulum will pass. So at A, it has potential energy EP given by mgh, right? So the potential energy is, of course, is relative to the equilibrium position, not the ground, but relative to the equilibrium position. Good. Now at A, the pendulum is stationary and therefore its velocity is equal to 0 and therefore its kinetic energy is equal to 0. So at A, the pendulum has no kinetic energy because it is not moving, but it has a maximum potential energy given by mgh. Now as the pendulum falls, or as it moves along this path here, it loses height and therefore it loses potential energy, right? So it loses potential energy, and according to the principle of conservation of mechanical energy, it gains an equivalent or an equal amount of kinetic energy. So at B, let me just make some space. So we know that B is the equilibrium position. So I will just make some space here, right? So at B, as it passes through B, the velocity is a maximum. So the velocity is a maximum and the kinetic energy is also a maximum, right? And in this case, the kinetic energy would be equal to the initial potential energy it possessed at A. Now at B, which is at lowest point, we say the potential energy, EP, is equal to 0. Now, you must remember now that we're talking about potential energy relative to this equilibrium position. So if it's at the position, then the potential energy relative to it will be 0. The initial potential energy at A is the potential energy relative to this position, and so we use the height h and not the height above the ground. Okay? So we need to make that clear. Good? So as it falls, it loses potential energy and gains an equal amount of kinetic energy. At B, it is at its lowest position, the potential energy is basically equal to 0, and the kinetic energy is at a maximum because the velocity is our maximum. All right? Now, as it moves from B to C, then this energy transformation or energy conversion will reverse. So at B, it has a large amount of kinetic energy, and as it rises to C, its height again is increasing, and it will therefore lose kinetic energy as it slows down, and eventually at C, it retains its initial potential energy, EP, equals mgh, and once again, the kinetic energy is equal to 0, right? So this is basically demonstrating the principle of conservation of mechanical energy using the simple pendulum. Now let's just assign some numbers. Let's say at A, the pendulum had possessed 100 joules of, say, potential energy. Now when it is at B, then the kinetic energy will be a maximum and will now be equal to that 100 joules, since of course the potential energy is equal to 0. So we see that at A and B, it has 100 joules of mechanical energy. At some point between A and B, let's say here, let's say it had 50 joules of potential energy. Because mechanical energy is conserved, then it must also have 50 joules of kinetic energy and so on. So whatever the value of potential energy, then that value and the kinetic energy must add to give 100 and so on. And again, once again, as it rises to C, it then loses that kinetic energy and regains its potential energy. So once again at C, it has 100 joules of potential energy and 0 kinetic energy. And once again, if there is some point, say here, where the potential energy EP is equal to 30 joules, then the kinetic energy, I'll put a larger number, let's say EP equals 70, then the kinetic energy will be equal to 30 joules because they must add to give 100 because mechanical energy is being conserved.